Alright, so today we're going to look at 12.2 Check Your Understandings. And we're going to start out with the transforming nonlinear data problem here. So you're a marine biologist interested in analyzing the lengths and weights of Atlantic rockfish. You and your crew will be going out to catch rockfish to collect data before releasing the fish. You're able to collect data on the length in centimeters and weight in grams for Atlantic Ocean rockfish of several sizes. Here's a scatter plot of the data. So our scatter plot set up over on the right hand side. Note the clear curved form. So we got a curved form to our scatter plot. Because length is one-dimensional and weight, like volume, is three-dimensional, a power model of the form weight equals A times length cubed should describe the relationship. Here's a scatter plot of the weight versus length cubed. So we got that down there below. Okay. As you see, our weight, we have listed right here, and our length cubed right there, okay? So because the transformation made the association roughly linear, we could use computer software to perform a linear regression analysis of y equaling the weight versus x equals length cubed. So we have, key thing to take away from this, our y is going to be our weight, and our x is going to be our length cubed, okay? So in part A here, it says give the equation least squares regression line and define any variables used. So in other words, I want you to define what your y and your x values are that you determined from this equation. Well, now also, let's look at the simple fact of our table here. We talked about this in 12.1. So for our y-intercept, we're going to have this value right here. Okay, that's going to be our y-intercept of 4.066. And our slope is going to be the value right here of 0.0146774. That is your slope that we're going to need to worry about. And again, your x value, right, is going to be your length cubed, because it tells us that in the problem right there, the last thing we underlined right there, right? That is your x value, right, the length cubed. So now we need to write the equation for this. Well, as we saw dealing at 12.1, you should have, okay, your y hat for your predicted value is equal to, and we like to write our y-intercept value first in this. So we're going to say 4.066, and we have a positive slope, so plus our slope value of 0.0146774. Okay, and then we have our x, because that's what we're talking about, x. Now the only other trick to this one is, it says x is your length cubed. So with that, I'm going to put, since x is representing our length, I'm going to make sure we put that as a cubed value there for it. So our x is cubed. Okay, so for this, we know, as I just said, our x is our length, so x equals length. Well, if I go right here, that's more. So your length, right, and y is your weight, which was given to us in the problem right up here, given us right here saying y is our weight and x is our length. But again, statistics, we like to write this stuff out again to make sure that people reading our answers know what we're talking about. Now the other thing says define any variables you use. So yes, we did do that by saying x and y. Let's go ahead and rewrite that problem and how it should look. So in other words, if your y is your weight, you simply say you have a weight, put a little hat on it, in which case that'll equal 4.066 plus your 0.0146774, and then we're going to have our length. And then that is cubed. And I'm going to go ahead and put that in a parenthesis there, just so that word doesn't look like it's all crazy with that. So the length is cubed, okay? So that is what the actual equation they're looking for is. Now, again, it's best to write it out with putting in your context part of this, right? The variables, what they are, as far as your weight is what you're solving for your y, and your x is referring to the length. This makes it a little bit easier to do problems like on part B here. So in part B, it says, suppose you catch an Atlantic Ocean rockfish that's 36 centimeters long. Use the model from part A to predict the fish's weight. So again, to get our predicted value here, we now have our x value. We have 36 centimeters. So our x is going to be 36 centimeters. Well, to do that, let's go ahead and figure this out. We know that our weight, okay, our predicted weight value for this is this equation right here that we just wrote out. So the 4.066 plus the 0.0146774, and then this times our x value they told us was 36. We're going to cube it. And when I did that on my calculator, I came out with, this should give us 688.9 grams. Okay, and again, don't leave off your labeling for the variables, right? So we have, labeling for your data values. So grams in their case, okay? In which case, that is your answer. That's what we're looking for. So the predicted value for an Atlantic Ocean rockfish that is 36 centimeters long is 688.9 grams. All right, so now let's look at the next section we have here for 12.2, in which case we're going to look at choosing the best regression. Okay. So in this one, many adults plan ahead of their eventual passing by purchasing life insurance. Many different types of life insurance policies are available. Some provide coverage throughout an individual's life, whole life, while others last only a specified number of years, term life. The policyholder makes regular payments, premiums, to the insurance company in return for their coverage. The table shows monthly premiums for a 10-year term life insurance policy worth $1 million. Okay, so that's what we have our little table over there, dealing with your ages and your monthly premiums. Now, the output shows three possible models for predicting monthly premium from age. Option 1 is based on the original data, while options 2 and 3 evolve transformations of the original data. Each set of the output includes a scatter plot with a least squares regression line added in a residual plot. The equations are given below. All right, so we have our A, B, and C little plots right there. And down here on number 1 it says, use each model to predict how much a 58-year-old would pay for such a policy. Okay, so 58-year-old is what we're looking at here. Now with this also, let's go ahead and just label what our A, B, and C data plots are according to these equations they gave us there, okay? So with that, we can look at our big ideas to do that. So again, to determine, most time with, if it's linear, it'll be x versus y. If the power is a log of y versus a log of x, or an exponential is log of y versus an x, okay? And for dealing with predictions and solving for these, like we did earlier, we just kind of plugged in our x to solve for y on the equation that we dealt with for the first part of 12.2. And this one we'll probably have to mess with dealing with some log and some natural log. So to get rid of your log, you would raise both sides to the power to 10, and then raise the answers to that power, okay? And then for the natural log, you're going to simply take an e and raise your values to e to the power of whatever the values you have, okay? And of course, if you have a cubed value, you can take the cube root. Hopefully you guys understand that for the most part. Okay, so we're going to look at these. dealing with this now, to check a scatter plot for linear pattern, when we're choosing the best regression line, shall we say, we check the scatter plot for linear pattern. We check the residual plot for no leftover pattern, which we've done the whole time. Residual plot, you got to make sure there's no pattern. It's got to be a good scattered layout. And the third thing is, if deciding between several good models, RNS can be used to decide which is best if all are good models. So dealing with your residuals and standard deviation of those other residuals, okay? So R is your residual values, and then S your standard deviation of the residuals. That can be used to determine which is the best fit for overall, if all the models are kind of in good standings. So let's look at these. So again, we had this set up for it saying A is just, looks like your values there written out, no natural logs or anything like that. So we're going to look at, we have simply a linear pattern overall. It's just a simple linear equation with that. So I'm just going to label this as linear. Okay. Now let's look at it. So we have natural log, and then going to our natural log of dealing with our x value, which is age in the equation there. So natural log of the premium equals negative 12.98 plus 4.416 times the natural log of the age. So as we saw here, we did this. We take the log versus log. In this case, we had natural log versus natural log. That was a power function, okay? So with that, our B is a power function. And for C, we have the natural log of the premium, and then it just looks like a linear style setup on the right-hand side, right? But we've got a natural log of our Y value. So with that, looking over here, that should be our exponential. In this case, it's a log of Y versus our X, in which case we have natural log of Y versus our X. So with that, we're going to say that our C is our exponential layout. Okay, so we got exponential. So now we're going to solve each one of these equations by plugging in 58 for our age. So if we put in a 58 for A value, and just put that in there, and we do the calculations, let's see what we get. All right, so we had a negative 3, well, I'm going to put negative there, sorry about that, negative 343, and then plus 8.63, and then that was times 58. In which case I got 157.54. So the premium, so for our premium, I got 157.54. Okay, so let's find out. That's for the linear pattern. Now, if we do a power pattern on this setup for it, let's see what this premium would be. So we're going to put a 58 in for this guy right there. Okay, so let's see what our value is that we get over here dealing with this all together for actual number value. When we take negative 12.98 and actually add 4.416 times natural log of 58. So we're going to take, we have a negative 12.98 plus 4.416, and then we're going to take the natural log of 58. Okay, so we get 4.95092. I'm just going to use 4.95. Looks like a good number to use to justify the actual answer here. So with this, we have natural log of the premium is equal to 4.95. Well, to get rid of that natural log of the premium and solve for this value over here, so we have a natural log of the premium equals 4.95. We need to take this, as we saw in our big ideas, to get rid of this natural log, we need to take both sides and raise them e to the power of the values we get on both sides, all right? So let's do that. So if we just simply do this, then let's see what we get now for answer, because that would give us, if we do this, therefore our solution then would be our premium. Premium would then, let's see what we get. All right. So if we take e to the power of 4.95, come out to get 141.175. Well, I want to simply say it's 141.18, right? 141.18. Now let's do the same thing with this bottom one for part C. So 58, and we'll plug this in and see what we get for a value over here on the right hand side. So we should get negative 0.063 plus 0.0859 times 58. Okay, so we should get 4.9192. Let's go ahead and use 4.92. Since we use just 4.95 on B, let's just keep it 2 decimal places on this part C as well. So we'll say 4.92. So for this side, we got 4.92. But we still have a natural log over here. So let's go ahead and take E, raised to power natural log, to get rid of that, of your premium. Okay. And that's the same thing, equal, or E, the power of 4.92. So therefore, we should get our premium, our predicted value here that we should get for this. So we take E, our 4.92, and 137.003, so 137 exactly. So 137. It's a horrible 3. Let me write that 3 again. 137. Okay. So those are the predicted premiums that they would pay. So you got 157.54, 141.18, and then 137 even with that. Okay. So with this, what type of function, linear power exponential, best describes the relationship between age and monthly premium? Explain your answer. So with this, let's look at these, because we've got apparently the best model for pay, if anything, would be an exponential. Let's look at this overall for our residuals and everything, looking at our linear power and exponential. So with this, I see in the residual, when dealing with a linear pattern, there is an actual U-shaped pattern in the residuals, and we don't want that. That means it's not a good fit for it. Same thing with our power here. Looks like it starts up high, drops down, does a little bump and comes right back up. So it's U-shaped as well. However, with the exponential, it's scattered. It's going, you got one below, one above, one below, one above, one below, one above. So it is an actual scattered setup for your residual setups, as well as the standard deviation. So those residuals are pretty well equal as well for balancing out the actual line to fit for least squares regression line. So with that, our exponential is the best fit for this because the residual plots show no leftover pattern. Okay, so for number 2, which function is the best? We're going to say exponential. right? Because the residuals, or residual plot, I should say, not just residuals, residual plot shows no leftover pattern, shows no leftover pattern, right? It was a good scattered pattern on the residual plot, so therefore that one works. And you can even say the other ones actually have a pattern in the residuals, but the overall explanation is the exponential is the best fit because the residual plot shows no leftover patterns. All right, which definitely covered the setup here when we're dealing with this, with our big ideas. With number 2, that's what it played out for the actual number 2 in our check understanding. Check the residual plot for no leftover pattern. In which case we did. In our exponential, in that one, had no leftover pattern in our residual plots for the least squares regression line to fit. All right, so hopefully that helps explain things a little bit better. Definitely look at the big ideas, review that, and grasp what it's looking at on solving for these equations, which is more of a calculus-based setup or a pre-cal dealing with using the natural log and solving for that. So hopefully it's not too overwhelming. With that, it's pretty straightforward with just taking both sides. E raise the power what you get on, or E raise the value what you get on both sides. And that should be able to solve and get rid of the natural log for you, okay? All right, well, I hope you learned a little bit of something today, and I'll see you next time.